thank everybody for attending this webinar, and thank Yupeng for inviting me. Thank you for thank all of the organizers for this webinar. I'm very happy to give a talk here. So yeah, today I'm going to talk about one part of my PhD thesis, which is titled Reduced Modeling and Global Instability of Low Reynolds Number Flows Through Compliant Microchannels. Before I get started, I would like to acknowledge a few people who have helped me during this research project. First of all, I would like to say a big thank you to my PhD advisor, Professor Ivan Christoph at Purdue University. And I also would like to acknowledge all of my colleagues in the TMNT lab at the Purdue University of Mechanical, in the Mechanical School of Mechanical Engineering. First, I would like to give a little bit of background of this research. So I am interested in flow through microchannels, microconduits, which is related to the nascent field called microfluidics. In this figure, I show a typical microfluidic chip. You can see that the chip is pretty small. Each of these lines here, either red or blue, represents a microconduit. Such conduits are very small. Its smallest dimension is comparable to a human hair. Therefore, a flow within such small conduits is typically very slow. The reported Reynolds number is up to several hundreds. Microfluidic devices are often made from soft materials. One of the most commonly used material is PDMS. The PDMS is very soft. Its Young's modulus is at the order of 1 megapascal. Therefore, it is easy to deform when subject to external forces. In this figure, I show a typical procedure of fabricating a microchannel using replica molding. I will not go into the details of this procedure, but I would like to highlight that each of these holes here actually represent a microchannel or macroconduit. If you enlarge it, you will find the most common configuration of a microconduit is actually a rectangular microchannel. So this gray slab here represents the deformable compliant wall made from PDMS, and the blue part is the conduit for conveying fluid. Right? Since the wall is made soft, and when a fluid is pushed through into the conduit, the flow pressure will make the wall deform, and the wall deformation will in turn influence the flow within, causing this feedback loop. Therefore, we say fluid structure interaction, FSI, is an unavoidable topic in this area. And actually, FSI has aroused many interesting phenomena in compliant microchannel systems, which cannot be observed in rigid channels. Today, I'm going to focus on one interesting phenomenon, which is low Reynolds number instability in compliant microchannels. In 2013, Worma and Kumaran conducted an interesting experiment. In that experiment, they took out a rectangular microchannel, and the microchannel was used to convey Newtonian fluids. What did they observe? So in their experiment, this is a side view of the microchannel. Instead of like our previous configuration, their bottom wall is made very soft, while the other three walls are made rigid. And they conducted a die stream experiment in this rectangular microchannel. What they observed is like when they increase the flow rate, they can observe the die break up at a very low Reynolds number. You can see that the reported Reynolds number for die broke up is just 200. And recall that in rigid channel, the well-documented hydrodynamic instability Reynolds number, critical Reynolds number for hydrodynamic instability is usually about 1000. Therefore, the reduction of the Reynolds number for instability in compliant channels must be related to FSI. And they also documented a few key features of the observed low Reynolds number instability. First of all, as I have mentioned, there is a transition from stability to instability when the flow rate is increased. And secondly, they always observed the instability occurred in the weakly inertia flow regime when the reported Reynolds number is at several hundred, or the reduced Reynolds number is at order 1. I will give more details about the reduced Reynolds number later. And thirdly, they always observed that the dye broke up first near the channel outlet. And lastly, they also reported that the wall, the compliant wall would oscillate when the instability occurred. And we would like to use mathematical modeling to understand why the low Reynolds number instability could happen in compliant channels. And we would like to test our models to see whether our mathematical model can reproduce these key features observed from the experiment. So let's take out our most commonly rectangular microchannel. There are a few important geometrical properties of this configuration. First of all, the channel is made very long and shallow, with its undeformed height much smaller than its width much smaller than its length. Therefore, the channel itself is like a pancake, shallow and long. The compliant wall is made very slender. Its thickness and width is much smaller than its length. Then the FSI problem within this configuration can be decomposed into coupling of two basic problems. First, the solid mechanics problem which concerns a rectangular compliant slab subject to non-uniform hydrodynamic pressure under its bottom. And the second problem is a fluid mechanics problem, which concerns a flow flowing through a spatially non-uniform channel. Let's first analyze the fluid mechanics problem. So we assume the fluid is Newtonian and the flow is incompressible. The deformed channel height is simply the undeformed channel height plus the interface displacement. We also assume in the deformed state, the deformed height is much smaller than the width, and the width is much smaller than the channel length. With that, we can introduce two small aspect ratios, delta and epsilon, to make our governing incompressible Navier-Stokes equations dimensionless. The leading order terms for the governing equations are shown here. For the first equation is just the conservation of mass in the flow. To ensure this conservation of mass, we have to pick the characteristic velocity scale for the three velocity components like this, which actually says like only the axial velocity Vz is the most dominant at the leading order, which means like the flow is almost unidirectional. And these two equations actually are the leading order X and Y momentum equations, which further indicates that the pressure varies along the flow-wise direction only at the leading order. And the last equation is actually the Z momentum equation. If you look at the right-hand side, it actually has a balance between the pressure gradient and the viscous stress. With these two, the balance of these two terms actually means the shear stress in the flow is much smaller than the flow pressure. Therefore, in our analysis, we view hydrodynamic pressure as the only external loading for the water formation. And for the left-hand side, it represents the fluid inertia. It has a scaling as the reduced Reynolds number, which can be written as the small aspect ratio epsilon times the regular Reynolds number. If the reduced Reynolds number is much smaller than 1, we can neglect the fluid inertia, and then we say we are in the inertialess flow regime, and then the Z momentum equation can be integrated directly to give you a parabolic velocity profile along the deformed height. if the reduced Reynolds number is at order 1, actually you will achieve a balance between the finite fluid inertia and the dominant pressure gradient and the viscous stress in the flow. In this case, you cannot integrate the Z momentum equation directly, and we will show you how we will deal with this situation. For the solid mechanics problem, we recall that the wall is made slender, and within the framework of linear elasticity, we also assume the solid inertia is pretty weak. This actually can be justified with scaling analysis in the microfluidic setting. We further neglect all of the body forces, then the governing equation for the solid wall deformation is simply the balance of Cauchy stresses. By doing a scaling analysis, taking advantage of the slenderness of the wall, we can show that the dominant Cauchy stresses components are the components living in the XY cross-sectional plane. And consequently, the dominant strains also live in the XY cross-sectional plane. Then, in this case, the original 3D elasticity problem can be reduced to a 2D plane strain problem in the XY cross-sectional plane. That is to say, we can take out each cross-section of the wall out and investigate its deformation individually. Each cross-section can be viewed as a compliant rectangle subject to uniform pressure on its bottom. And depending on the configuration of the micro-channel system, you can actually apply different boundary conditions at these 3 surfaces. No matter what, you can show that the interface displacement UY actually has a general solution which is written in this separation of variable form. If you look at this solution, you can see that this is actually saying the interface displacement at a particular streamwise location is fully determined, is proportional to the local pressure P. This is actually like a Winkler foundation. You can thus imagine the interface is sitting below a bunch of springs. Those springs have variable stiffness along the spanwise direction X, and at a specific location, the displacement at that location will be determined by the local stiffness of your spring and the local pressure. Then the rest of my talk will show you how we couple fluid and how we couple the fluid mechanics problem with the solid mechanics problem. And the key step here is we reduce the system by with averaging. By doing that, we end up with a 1D wall deformation equation and a set of 1D flow equations at Reynolds number up to order 1. Then by coupling these 2 sets of equations, we end up with a new 1D FSI model. So for the fluid mechanics part, if you with averaging everything, actually your 3D microchannel will become a 2D microchannel looking like this. This actually does not change any key statements made before because this average deformed height is still much smaller than the length of the channel. Therefore, lubrication approximation still applies. That is saying, like the leading order terms left in your 2D Navier-Stokes equations is just the original 3D version getting rid of the X-dependent terms. And when the Reynolds number is at order 1, you can still achieve a balance between the finite fluid inertia and the dominant pressure gradient and the viscous stress. We will invoke one common Paul-Hausen approximation to assume the dominant axial velocity Vz has a parabolic velocity profile along the deformed height. Then by applying kinematic boundary condition at the interface and also no slip boundary condition at the interface and the bottom wall of the channel, we can integrate the leading order terms left in the 2D Navier-Stokes equations. At the end of the day, we end up with these 2 1D nonlinear flow equations. The first equation is just the integrated version of conservation for mass, and the second equation is the graded version of conservation of linear momentum along z direction. We can do the similar things for the solid mechanics problem. For the solid mechanics problem, if we do a width averaging, the 2D Winkler foundation will become a 1D Winkler foundation. That is saying, like, because we average over x, the variable stiffness k will become a constant k bar here. And in this case, the displacement will still proportional. The interface displacement is still proportional to the local pressure, like a Winkler foundation. But if we only consider the Winkler foundation like a behavior of the interface displacement, this will give rise to a problem, because channel flow is usually pressure driven, which means the pressure at the channel outlet, at the channel inlet is non-zero. If you have a non-zero pressure at the inlet and your interface is deforming like a Winkler foundation, then you can deduce that the displacement at the channel inlet should not be zero. But this is actually contradictory to what contradictory with what we see in the experiment. This is the deformed interface shown in the experiment. So you can see that at the channel inlet, the displacement at the channel inlet is actually constrained zero, because the channel is usually needed to connect to some rigid part. That connection actually constrains the displacement of the wall at the inlet. Therefore, that's why in our 2D channel, we also constrain the displacements at the two ends. Then what do we do to make our 1D system can satisfy this kind of boundary constraints? Well, we think of the interface displacement problem like a boundary layer problem, while the Winkler foundation like behavior is like an outer solution, weak and dominant in the system. We can consider some other weak deformation effects. With those weak deformation effects, we can introduce some inner solutions near the channel inlet and outlet to help the system satisfy the boundary conditions. Since the bulging of the interface naturally introduce axial stretch along z direction, therefore weak tension is a common choice. Therefore, we can write out a 1D wall deformation in this form. So this third term here actually represents the weak tension, and the chi t here is the width average constant tension, and we have a determined formula for computing that. This second term here is actually represents the dominant Winkler foundation like behavior of the wall deformation. Since we are interested in the dynamic response of the microchannel system, we will also consider weak solid inertia, which can be written in this form. Here, B star is the effective interface thickness, and we also have a determined way to compute that. To this end, we have finished modeling the FSI system. We end up with these 4 equations. We can also pick appropriate scales to make the system dimensionless. At the end of the day, we will have 3 new dimensionless parameters. First of all, beta, which is the FSI parameter. Beta is defined as the characteristic displacement scale divided by undeformed channel height. In our analysis, beta is typically an order 1 quantity. If you look at this equation, beta is actually gauging the fluid solid coupling strength. That is saying beta is actually translating the wall deformation into the deformation of the fluid domain. Theta I here is the solid inertial coefficient. With the framework of our scaling analysis, we can show that theta I is a small quantity, and the theta T here is the tension coefficient. Theta T is also a small quantity because we require that to be small to ensure the boundary layer like behavior of wall deformation. Next, I will show you some simulated results of the 1D FSI system. For this 1D FSI model, we apply a few boundary conditions and initial conditions. We fix the flux at the channel inlet and set the channel outlet pressure to gauge. For the displacement at the both ends, the wall are the displacement at both ends are restricted to be 0. And as for the initial conditions, we consider uniform flow under undeformed channel height. This set of equations can be solved with Chebyshev pseudospectral spatial discretization combined with numerical beta time integration. And at each time step, we will face a nonlinear system. And that system can be solved using Newton-Curlow methods. The example case we chose is the commonly seen thick-walled microchannel with its properties, geometrical properties, and material properties tabulated in this table. And this is how we calculate all of the non-dimensionalized parameters. We pick two cases. One case is low flow rate case. The reduced Reynolds number is much smaller than 1. The other one is high flow rate case. The reduced Reynolds number is at order 1. In this figure, the thick black line represents the fluid solid interface, and each of these sub-panel represents give you a zoom-in view for the interface dynamics near the channel inlet and outlet respectively. As you can see, as I turn on the flow, for the low flow rate case, the interface just bulges steadily towards the steady state. However, if I turn on the flow for the high flow rate case, something different is happening. You can see that the interface first bulges up, and at the same time, you can see transverse waves shed from the channel inlet and propagating towards the channel outlet. After the waves hit the right boundary, they will get reflected, and the incoming waves interact with the reflective waves, which give rise to another kind of transverse wave with shorter wavelength. These waves keep propagating back and forth along the fluid-solid interface, and you can see that the system is not reaching the steady state. And now, if you pay more attention to the channel outlet, or if you look at this sub-panel here, after a while, you can see that the oscillation in this region become more and more violent. And let's recall some key features we observed in the experiment. And you see that in our 1D FSI model, we also see that there is a transition from stability to instability when the flow rate is increased. And secondly, we observe the system doesn't want to reach the steady state when the reduced Reynolds number is at order 1. That is to say, the flow is in the weakly inertial flow regime. And thirdly, we observe in our simulations, the wall oscillations near the channel outlet is more violent compared to the channel inlet. This might be related to the experimental observation that the die always breaks up first near the channel outlet. And lastly, in the unstable case, we also see like the wall oscillate very violently when the system doesn't want to reach the steady state. Therefore, our 1D FSI system can capture these 4 key features observed in the experiment. We would like to know why in some cases the system doesn't want to reach the steady state. Therefore, we would like to answer that question, we would like to analyze the stability of the steady state. For this 1D FSI model, since the channel flow is pressure driven, there is a non-uniform pressure distribution within the flow. Therefore, the deformation at the steady state is also non-uniform. There is a short diverging section near the channel inlet and a long converging section towards the channel outlet. To conduct a linear stability analysis with respect to this non-uniform steady state, we have to make our eigenfunctions dependent on the spatial coordinate z. Therefore, we have to do a global analysis for this problem. Within this formulation, if the imaginary part of the eigenvalue is greater than 0, we will have instability. And we substitute this perturbed steady state back into our governing equations and do a linearization. We end up with this generalized eigenvalue problem. This problem can be solved with the Chebyshev pseudospectral method with modified Lagrange polynomial basis. And for these two simulated cases, you can see that for the low flow rate case, the reduced Reynolds number is much smaller than 1, and the corresponding eigenspectrum always live in the lower half of complex plane, which means this case is linearly stable. However, for the high flow rate case, when the flow is in the weakly inertial flow regime, we do detect a few unstable modes living here. Therefore, in this case, we find the steady state of the second case is actually linearly unstable. If we can also extract the eigenfunctions of a few unstable modes, what we observe is that the eigenfunction has interesting shape. The shape changes more dramatically near the channel outlet. That could explain why the oscillation near the channel outlet is more violent, which further explains the experimental observation that the dye always breaks up first near the channel outlet. And we can do more analysis. We can further take out our solid wall deformation equation. Since the tension coefficient theta t is much smaller than 1, the natural frequency of the wall can be estimated using this formula. For the unstable case we just simulated, we find all of the unstable modes actually have a frequency very close to the have an oscillatory frequency very close to the natural frequency of the wall. This suggests that the observed instability is actually a resonance phenomenon. We can also plot our wall velocity history from our simulation and do a Fourier transform for the corresponding time histories. You can see that the wall oscillation also has a peak frequency very close to the natural frequency of the wall. Recall that in our simulation, in our initial conditions, we have never introduced any oscillatory components. Therefore, these oscillations experienced by the wall must be triggered by FSI. To this end, we can give a new explanation for the observed low Reynolds number instability. That is to say, FSI can trigger wall resonance, giving rise to self-sustained oscillations in the wall and leading to unstable flows at the microscale. For more details, please refer to our preprint, and also this paper will appear in Journal of Fluid Mechanics soon. And to this end, I'm happy to take any questions. Thank you for your attention.